All right, everybody. So I haven't posted the key to the conversions homework yet. That'll go. I'll put out an announcement on Canvas. It'll have the key attached to it later this afternoon. Also, I heard that the assignment wasn't visible for you to submit for that one yet. That should be fixed now. The due date's set for Thursday, so it should show up in your to-do list and should have a place to submit that assignment. So all that should be good to go now. So with that said, we'll get into your quiz questions. So normally with the quiz questions, I'll just take a couple of the quiz questions and answer them. Since this is the first time, I'm going to try to answer as many of them as I can in a reasonable amount of time. Just because, especially, and I'll always try to get anything that's relevant to this course. So if you ask me a specific question about an assignment, or about grading policies or anything like that, I'll always answer those in class to make sure everybody hears it. Because if one person asks, then probably more of you have that same question, or would if you had thought about it. So I'll pretty much always try to answer all of those if possible. So sometimes that means we're a little bit front heavy, answering the questions before we get into new material. But that's usually to your advantage. So questions about the class from the quiz. If you miss due to a sport or anything really, it doesn't really matter. There is opportunity to make up most assignments. So all of your assignments can be submitted on Canvas. So there's really not a reason that you should be late on any assignments when it comes to missing for a sport, right? Because you can always just submit it online. As long as you've got your backpack and access to the internet, you should be able to submit your assignments. When the trickiest part comes with labs, because that involves some time that you have to be here and do an activity here to do most of the labs. Most of those you'll be able to make up, especially if you arrange with Tom's or I ahead of time. We'll set up, usually most of our labs are going to be on Thursdays. So if you miss a Thursday lab, you can make it up on the following Tuesday usually. Just let us know ahead of time. There might be a couple of exceptions for things where either I had to bring stuff from the college or the stuff that has lots of prep that has to be done in advance on our end. Some of those assignments, those labs just aren't really feasible to make up at a different time, but you do get to drop 2 assignments in the assignments category to account for the fact that some of you might not be able to make up some of the labs. So if you do miss a lab and it's one of the ones you can't make it up, it'll probably just be your drop assignment and it shouldn't affect your grade beyond that. All right, so as long as you only have 2 of those, then it's not going to really affect your grade too much, which I think will cover everybody, because the odds that you miss that more Tuesdays or more Thursdays and there all happen to be labs that you can't make up, that's probably a pretty low probability that that'll happen. But that said, there's always an exception. So if you have any other questions about that, just ask us and we'll talk about your specific situation. The way office hours work is I don't really have office hours here, but if you came to the college for my office hours, then office hours for any college class just means it's open. Some professors do prefer you let them know ahead of time, but at the college, we're always there. We're always present for our office hours. So any other college class you have, if you know your instructor's office hours, you can always drop in. If it's something out of the ordinary, if you don't normally see them over at campus over there, you might want to make an appointment with them. Just email them to let them know, but it's not required. It's definitely not required for my office hours. I might just be out and about. So it might take a few minutes if I'm out helping another class or talking to somebody on campus. A lot of you want to know what's something that you can do to help prepare for this class. There's a lot of good resources out there. The number one resources I would say as we get into the class, especially if you like YouTube and videos, Khan Academy, which I'm sure you've heard before, but Khan Academy actually excels at chemistry. Khan Academy got started because Sal Khan was trying to tutor his niece in organic chemistry from across the country. So organic chemistry specifically, but chemistry in general is something Khan Academy is really good at. So those are really useful resources. And then there's another channel that I recommend all the time called Professor Dave Explains. Professor Dave Explains. He explains things really well. He's a pretty funny guy. He's entertaining, makes pretty good graphics and things like that. So if you're looking for other sources that can help you with this, Professor Dave Explains and Khan Academy are probably the number one and two sources I would recommend. Beyond that, advice for this class is stay on top of the due dates. If you're anything like me, then as soon as you get overdue in 2 or 3 assignments, it starts feeling overwhelming, even if you've got them most of the way done. I would highly recommend, if you're almost done with an assignment, but it's going to be late and you're not going to have time to work on it, it's almost always better to turn in something on time. I still want you to ask if you got stuck on something, and you can always resubmit. You can submit your assignments more than once, and I can see all of the submissions. So if you got 9 out of the 10 problems done and submitted on time, and then you went back to finish the 10th problem, if you're the type of student that can remember to do that, then I'll look at both of those, and I'll give you whichever grade is higher, either the on-time grade or the late but complete grade. However, if you're a type of student where having a couple assignments overdue will start to pile up and then spiral, just turn in what you have done. It's better to get 6 out of 10 on every assignment by turning it on time than it is to get a bunch of zeros because you got overwhelmed. Right? So stay on top of those due dates. Stay on top of the assignments as much as you can. That's my number one piece of advice, especially among the high school students that I've had before. That's the number one reason people fail this class. It's not because they don't understand the material. It turns into that by the end, but it's mainly because they start to spiral when they get behind. And so don't get behind. Stay on top of things as best you can. It's easy for me to say up here because I'm the one making the assignments, but try to stay on top of it, and that'll help you a lot. And then there is a bunch of tutors at the college, and I have the link that's in the slides here. Oh, wants me to update the browser. Is to a Google Sheets that has hours for a bunch of the tutors at the college. Anybody that has CHM in their description means that they tutor in chemistry as well. There's a number of people, and a lot of people that are listed as math tutors will also work for chemistry as well. And next time, I guess I'll screenshot that and link the screenshot, since this doesn't work that well. This is also a good example of why when I ask you to submit like spreadsheets or any sort of digital files, don't send me a link to your Google Drive, because that doesn't work through Canvas. When you do that, it won't give me access to it, and I still won't have access to that spreadsheet or that file. Download the file and upload it to Canvas, and then I can actually see it. And because this is exactly what happens. It just doesn't work when you try to link things in Google Drive, and try, especially if you put it through Canvas. Yeah, I'm not going to reinstall the browser right now. Chemistry questions from the quiz. Why does the amount of sig figs matter for rounding? We'll talk in more detail about the rules for rounding. But on a general sense, the amount of sig figs matters because whatever the last digit you report, you're supposed to assume that the number is plus or minus 1 in that place. So if I write 73 hours, if this is a measured number, that 73 hours is assumed to be plus or minus 1 hour. If I write 73.0 hours, it's assumed to be plus or minus 1/10 of an hour. Right? So knowing where to round is communicating where the uncertainty is to the reader. And so counting the number of sig figs or when you're multiplying, and you want to say, okay, if I'm going to say 73 hours and it's 65 miles per hour, actually make the math easier. Never drive this fast, but assume it's 100 miles per hour, whatever it is we're talking about. Our answer would be 7,300, right? 7,300. We still only want to keep our uncertainty in the spot in the second sig fig, in the second significant digit. So we'd say 7,300 plus or minus 100 miles, or to avoid having an ambiguous number, 7.3 times 10 to the 3 miles. Having two sig figs means that your uncertainty is 10% or approximately 10% of your total value. So you keep that 10% of that total value when we multiply it. And that's why we have rules for this. We wouldn't just want to say 7,300 plus or minus 1 mile, because that's way more accurate of a number. That has a way smaller uncertainty relative to the entire measured number. Then our uncertainty is only 0.01% of the total number instead of 10% of the entire number. Right? And so that's why we have these rules for rounding. I'll give some examples with the addition and subtraction rule that kind of help it make sense. And then we're just going to have sort of two rules, one for addition, subtraction, one for multiplication and division. That's going to kind of help us make sure we keep the uncertainty to a reasonable level. The second question here was an oddly specific question. I'm not sure what about bananas specifically this person was referring to, but most things that live have very, very similar chemical composition. The specific hormones, the specific neurotransmitters, the specific energy storage molecules might be slightly different, but for the most part, anything that lives uses ATP for energy, uses DNA for information storage. So there's usually there's a lot of enzymes that are really, really similar. So I don't know if this question came from, humans share 90% of their DNA with bananas or something like that sort of stat. That's usually pretty accurate because almost everything comes from a similar ancestor or comes from the same ancestor if you go back far enough, which means we share a lot of the same molecules. Common misconceptions about chemistry. I don't want to say that it's hard because it can be hard. It is complicated. But it's not something that has to be hard. Chemistry traditionally got used as a gatekeeping class, as a way to make sure that only people that went into the sciences were the people that belonged, which for the most part meant white males. If you weren't a white male from an affluent background, then you had trouble with the way that chemistry courses were designed. And that was, whether or not it was a conscious decision, it was definitely built into the way that the courses were structured. And it doesn't need to be that way. Everybody can understand chemistry. It's not one of those, it's not a topic that you either get it or you don't. Depending on your background and your interests, it might take more work for some people than others. But that doesn't mean that some people are destined to be good at chemistry and other people are destined to be bad at chemistry. So I'd say that's probably the number one misconception, is that you either get it or you don't. No, it's something you have to work at. And we're trying, at least in our department at the college, trying to get away from that idea of chemistry as a gatekeeping class. It's a hard class. Organic chemistry in particular gets thought of as a gatekeeping class because it's where a lot of pre-med students will hit organic chemistry and decide, maybe I don't want to be pre-med anymore because this is a lot of work. And so it winds out being a weed out class, but it doesn't have to be. And so that's, I would say, is the number one misconception. Chemistry related books. Let's see. actually, if you're into the health sciences at all or forensic science, I highly recommend a book called Poisoner's Handbook. It's written about the basically the invention of forensic science in New York in the 1920s and 1900s. It's really, really good because basically up to that point, there was no way to really test to see if somebody was poisoned. If they died unexpectedly, the best you could do was feed their last meal to a dog. And if the dog died, then they were probably poisoned. That was the level of forensic science in the early 1900s in the US and worldwide. There was a couple of chemists in New York City that actually started developing tests for specific toxins. That's actually where most forensic science came from. It didn't help that until that happened, coroner, which is the person who's responsible for determining cause of death, coroner was a politically appointed position. So basically, whoever paid the most to the governor or to the mayor would get appointed coroner. And that usually meant that was actually really an advantage for people that owned funeral homes. So basically, you would just pay to get appointed coroner so that you could send all the dead bodies to your funeral home, so that you could get paid for embalming them and preparing them for burial. So really, there was no reason to actually care about cause of death for these coroners. They just cared that the bodies went to their funeral home. So all that to say, that's a really fun, if you're into dead bodies, I guess, book about chemistry is Poisoner's Handbook. Uncle Tungsten is another good one. I also highly recommend Richard Feynman's memoirs called Surely You're Joking, Mr. Feynman. He's a physicist, not a chemist, but he worked on the Manhattan Project, so it kind of evens out. The Manhattan Project had a lot of chemistry, and he writes really well, and he has some very good stories and explanations about life. Everybody wants to know how, when, why did I wind up pursuing chemistry and or teaching? I think I got this in 6 different versions of that same question, which is fine. I always get this question a lot. I like chemistry because chemistry goes into everything. I picked chemistry because when I was in high school, I got to light stuff on fire in chemistry, and I thought that was a lot of fun. It was a lot less boring than some of my other science classes, when we got to make explosives and then take them outside and blow them up. I'd be lying if I said that there's anything really more to it than that at some level. I also just had a chemistry teacher that was a lot of fun. And I got into teaching because I like talking about chemistry more than I like doing research. Turns out I'm really bad at doing research. My personality and my interests and my ADHD really struggled in grad school because I'm just not, it was not something, and it didn't help that I had a really, really toxic PI as my boss. So I went into teaching because I like talking about science. And I think it helps my family a lot because I think my wife would have strangled me by now if I didn't have somebody else to talk to about science, because I'd be talking her ear off at home all the time. So it helps everybody that I teach science. If I didn't study chemistry, what would I have picked? Probably either aerospace engineering or creative writing. I really liked writing. I really like literature and books and movies and music. But chemistry seemed like that was something that would be easier to find a job, less competitive anyway. So I went with chemistry, and then I just do a lot of literary analysis in my spare time, just for fun. Let's see, what's else? Personal questions. I already mentioned my chemistry teacher in high school. He was probably my favorite. Somebody asked, what's my favorite D&D story? That's a fun one. It's not a particularly one incident, but when they were 7 and 9, I was playing Pathfinder with my kids, and they realized that they didn't have to just go into the room and start trying to fight everything. They started learning how that they could stretch the rules, sneak around, sneak in through a window, try to convince people of things instead of just walk into the room and hit them with the sword. And they had a lot of fun with it. And it was with a really cool cartoony adventure story that it also gets into my love of classic cinema. It's called A Fistful of Flowers, where they get to play as anthropomorphic sentient plants. So one of them was a dandelion and one of them was a fungus, and they had a lot of fun with it. Technically, I know fungus is not a plant, but it is for the purpose of this game. So I thought that was a lot of fun. It's the sort of thing that you only really see in tabletop games. Even video games can't really capture that well. If I picked one meal to eat for the rest of my life, probably sushi. Like sushi's varied enough. If money is not an object and I have access to good sushi, I would say sushi, because some days it could be fish, some days it could be just rice. There's a lot there. More likely, though, it would be pizza, because I eat pizza a lot because it's cheap and satisfying. And who doesn't like pizza, right? Don't tell me if you don't like pizza. Just pretend like you like pizza. Somebody asked about specific video games. I play video games that you can pause and walk away from. I don't play video games with other people anymore because I have small kids. So when I play video games, it's like I have 10 minutes to myself. I'm going to play a video game, and then 8 minutes into that, I have to go change a diaper or pick up a kid or things like that. So I don't play a whole lot of modern video games. I play older video games for the most part. Favorite concert I've been to. I have a lot about music on the next one, but favorite concert that I've ever been to. I had one for this. I used to live in San Diego, and I got to go to a lot of really good concerts. Actually, Dashboard Confessional put on a really good concert that I took my then girlfriend to, now wife, to when we just started dating. Anybody know the band Fun? We were young. That band, the lead singer of that band was in another band called The Format when I was in college, and The Format opened for Dashboard, and it was a really good show, a lot of fun. I went to an Audioslave show, their second tour, when they played some Rage songs and played some Soundgarden songs, and that one was a lot of fun too. That's it. Most of my memories are really small metal bands from San Diego that most people haven't heard of. He Is Legend. Anybody know the band He Is Legend? Every once in a while, somebody will raise their hand for that one. They put on a really good show. Couple other people asked what my answers were to the various questions. So I'm just going to throw this up there. There's a bunch of links on there for different types of music. Take the scattergun approach here. Hopefully something up there is somewhat related to something you're interested in, so we can bond over that. You can feel seen and have something to talk about with me. I've noticed as I get older, I get more and more weird with my taste in music. It used to be fairly middle of the road because I was hearing everything for the first time. And as I continue to find more and more new music, it tends to be more and more out there. But if any of these words sound interesting to you, I highly recommend these particular songs. And if you want to talk about any sort of music, obviously I have a pretty wide range of tastes, and I'm open to hearing lots of new stuff. So thank you for all the good suggestions too on the quiz. Yeah, same for movies and books. Basically, anything that takes itself too seriously, I probably liked it at some level. Anything pretentious, little snobby, that kind of usually fits with my taste in music and movies and books. This one, if you want an out there comic book, a graphic novel, Day Tripper, takes place in Brazil. It was originally written in Portuguese. But the translation's pretty good. Art is really, really good, and it's a really weird sort of magical realism in a comic book form. It's also like everyday life. Highly recommend that one. It's a lot of fun. And if you like fantasy stuff, Fifth Season. It sort of toes that line between fantasy and sci-fi. Very, very fun. Highly recommend. I have most of these books, and I'm willing to lend them out as well if anything sounds interesting to you. Let me know. I have a lending library that I keep in my office at the college, but if you anything specific that you're into, let me know and I can bring you a book you can borrow. All right. Well, now to the less interesting stuff. perhaps. Let's talk about measuring numbers. We didn't get to this on Friday because we were talking about the word problems and everything. When we're measuring numbers, we already talked a little bit about sig figs and uncertainty, but let's get into the actual why and how it works. Anytime you measure a number or have a measured number, you're not actually certain about that number. That's sort of the definition of a measured number, is that it has uncertainty associated with it. Now, not all numbers have uncertainty. If I say a foot is 12 inches, is that 12 inches? Does that have uncertainty associated with it? No, it's not about 12 inches. A foot is defined as 12 inches, right? It's not 12 inches plus or minus an inch. So some numbers, especially definitions like that, are exact numbers. But for the most part, more numbers that you'll run into are going to be measured numbers. And the other way you can think about measured numbers is anytime if you added more decimal points, you could get a more accurate number. So if I said 65 miles an hour, that's a measured number, right? Because I'm probably not actually going 65 miles an hour. I'm going 65.1 miles per hour, or 65.09 miles per hour. The fact that I can keep adding decimals and get more accurate tells you it's a measured number. The obvious place is if you're actually measuring it using your eye, then it's going to be a measured number by definition too, right? If I told you to measure the length of the piece of wood in A, how would you write that down? 4.5 centimeters. Yeah, how do you know to put 0.5 on it? Right in between 4 and 5. Is it, do you know it's 4.5? We can know with, I think everybody 100% in this room would agree with no uncertainty, it's between 4 and 5, right? Everybody would look at that and say it's 4 point something. Yeah, depending on your angle and the TV, especially if this was an actual object, we might disagree, is it 4.4 or 4.6 or 4.5, but we're all going to agree it's 4 point something, right? So when we measure a number, you're always going to write down as many numbers as you're absolutely certain about. And then you go one decimal place past that. Right? So 4.5 is absolutely the right way to write this number. We're absolutely certain that it's 4 point something. And then we're guessing that it's 4.5. We might be off by 10%. Might be off by a 10. Right? So that's our general rule. Anytime we measure a number, is you go one spot past the last number you're certain about. So any measured number, if I wrote 64.09 miles per hour, what I'm saying there is that these three numbers, I know with absolute certainty. Kind of. I know that I'm not off by an entire 10th. I might be off by 100. Is that how speedometers actually work, though? No, no speedometer is actually that accurate, at least not in a commercial car, right? So most speedometers only report numbers to the ones place, if it's a digital thermometer or a digital speedometer, or you have markings for the individual miles per hour, right? You might have, if it's 60, 70, that's not actually that bad. So if the needle is pointing right here, we'd still have to use some estimation there, right? Let me put the angle here better. So if that's where the needle is pointing for the speedometer, how would we read that? How would we measure that number? we can all agree that the point of the needle is less than 65, right? But it's more than 64. So we have marking, and we can agree on that because we have markings for every mile per hour. We have base 10 decimal markings. It's weird to say decimal considering we're talking about the ones place, but decimal in this case just means base 10. Means that we have markings for all 10 of those miles per hour in the ones place. So we're certain that it's 64 point something. And then we would estimate one spot past that. It looks kind of like it's about 3/4 of the way, right? Can I write 64.75? No, don't think in terms of fractions. Again, we talked about how the human brain is built around numbers and doesn't really do well with anything outside of a third to 3. Your mind instinctively will turn this into fractions because we think in whole numbers better than we think in decimals. If you say, look at that and say, that looks like it's right on the money, 3/4 of the way between 64 and 65, you have to pick 64.7 or 64.8. You can't write 64 3/4 or 64.75. Pick one. Doesn't matter which, because your last digit has uncertainty associated with it. So all you have to do is just pick something. 64, if you don't beat yourself up about trying to get it perfect, it's 64 point something high. So 64.8 is good enough. Right? And we would never write to the hundredths place because that's saying we're absolutely certain about the tens place, which we can't be in this situation. All right, and that means sometimes just changing the measuring tool is going to change your measurement, change the number you write down. So for instance, A and B, that piece of fake wood that's drawn there is the same length. Which is weird because your brain looks at A and immediately says that's exactly halfway between 4 and 5, right? I think everybody would look at that and say that's right on the money, 4.5. But as soon as you take that same object and add the decimal markings for the tenths place, now we can all see it's definitely not right on the money, 4.5. It's actually closer to 4.6. So if we were writing down the measurement for B, we'd be able to go one step further. Right? 4.58 or something centimeters. Right? So changing your measuring tool changes how many decimals you get to write a lot of the time. And that's why we have different types of glassware for measuring different amounts. We look at the glassware in the back over here. This is a graduated cylinder for measuring volume. It has markings for every milliliter. So we'd be able to estimate to 1/10 of a milliliter. This is a graduated cylinder that's got markings for every 1/10 of a milliliter. So we actually get to estimate to the 100th of a milliliter. Just by changing what vessel we're using to measure stuff changes how many digits we get to write. And that's the whole point of this week's lab. You guys will actually measure stuff using different tools. Sounds really, really basic, and it kind of is, but kind of underlies how a lot of things work when it comes to sig figs and uncertainty. So you'll literally start by, here's a ruler. Measure this shape, measure this object, and report. And it's not about the measurement, it's about you giving me the right number of digits for the ruler that you're using. All right, so here's an example of, say, a protractor. If you're using a protractor. So if we're measuring this angle, so in math, they don't really get this when you first are taught how to use a protractor. They actually don't teach you the rules for how to measure stuff, do they? They say, here's a protractor. Report what the angle is. In this case, if we're measuring this angle, what would we measure it as? 47. Everybody can look at that if you can count. If everybody has their glasses on or can get close enough, we can all agree it's between 47 and 48. So could we be off by an entire degree? No, we know that it's between 47 and 48 with certainty. So we'll write 47, and then we'll estimate that last digit. If it's between 47 and 48, it looks like it's right on the money, 47.5. Otherwise, to me, that looks a little bit under, so I'd say 47.4. But it's got uncertainty in it. That's the whole point of knowing where to stop writing digits. Is anybody reading this who knows these rules will know that this is plus or minus 0.1. Now, in some cases, you'll wind up with certain pieces of glassware will actually have uncertainty printed on them, especially cheaper glassware. It might actually say plus or minus 0.2 milliliters instead of plus or minus 0.1 milliliter. If it's explicitly written, then you don't go with that standard rule. But the general rule is whatever the last digit written in a measured number could be off by as much as 1 in that place. All right, and so that means that if we want to be really, really explicitly clear about our uncertainty, we can write it out. You can say plus or minus 0.01 centimeter.
So a lot of times when we're doing calculations, they'll come to me and say, I got 4.59.
Mm-hmm.
Is that within, like, would you accept that answer because
yes.
It's within 60?
Thank you. Yes, when you're doing a calculation, depending on where you rounded when you were writing it out, if you kept every single digit in your calculator and your calculator kept it out to 100 decimal places all the way through a multi-step calculation, you might get something different than somebody who hit enter on their calculator every step and rounded every step. But it should still be within that same range of uncertainty, maybe off by as much as 0.02. But I would consider those to be the same answer. If somebody got a calculated answer of 4.58 centimeters and somebody else got 4.61 centimeters, you probably both did the math the same way. You just rounded at different points. And so I would consider that, as long as it's the same number of digits that you wrote, I would consider that to be the same answer. DM? So usually you want to keep all the decimal points until the end and round at the end, with a caveat. And somebody asked me about this after class on Friday. If you have to switch operations, meaning if you go from a conversion where you're doing all multiplication and division, and then your next step involves you adding and subtracting has different rules for where to round that we'll talk about in a few minutes. You have to do your rounding before you switch from multiplication to addition because it's two different rules. So anytime you switch, and that's why I say when I say switch operations, I mean operations like order of operations from math. If you're switching from addition, subtraction to multiplication, you've got to round before you switch. And if you're switching from multiplication back to addition and subtraction, you've got to round before you switch. Make sense? We'll do some practice with that too. Did I see another hand? Did I answer? All right, one more practice here. We've got a graduated cylinder with markings for every milliliter. How many decimal places should we write, or what place should we write our measured number to? To the 10th place. We can be certain about the ones place, and we're going to estimate the 10th place. Right, so if we're reading that, how do you read liquids when you're measuring the volume of a liquid? It is, if it's water, it's at the bottom. Technically, it's at the flattest part of the meniscus. Some liquids in some vessels the meniscus will actually go backwards. If you put mercury in glass, the meniscus actually reverses. And so with mercury, you measure from the top of the meniscus. But with water in glass, you measure from the bottom of the meniscus. But the true rule is you measure from the flat part of the meniscus. So if we're measuring here, that looks really close to 43, right? 43 point something. You'd say 43.1. You'd say 42.9. Well, but if it looks like it's right at 43, how do we indicate the uncertainty? We add the 0.0. We're estimating it to the 10th place. So even if it looks like it's right on the line, we're not putting the 0.0 in there because it's going to affect our numbers in a calculation, right? We're putting the 0.0 there specifically to tell the people reading our number that we estimated that spot. Because if we just write 43 milliliters, that's saying it's plus or minus an entire milliliter. We don't want to do that because we actually worked harder than that. It's not plus or minus a milliliter. We got plus or minus 1/10 of a milliliter. So we write 0.0. Right? And same is true with your calculated numbers. If you need 3 sig figs when you're done with the calculation, and your calculation comes out to be 5 exactly on the calculator, you add 0.00 to say that's 3 sig figs. It's plus or minus 0.01. Right? Occasionally, you'll actually get an exact number in your calculator when you do these. You still need to make sure you remember to add the right number of zeros in that case. All right, so questions on measuring stuff. What about if it's something digital? How are you supposed to estimate the last digit if it's something digital? Like you put it on the scale and you've got, and the scale says 7.251 grams. Am I supposed to add a 0 to indicate the last one's estimated? Why not? Because the programming takes that into account already. So this is already showing you where the uncertainty is. It's plus or minus 1 in that last digit. Right? So don't add, but just because it came out of a computer or a digital display, don't assume that it's perfect. It's still a measured number. You just have to trust that the people that programmed that machine, that instrument, knew what they were doing when it came to displaying the right number of sig figs. And for the most part, they do, at least in a lab classroom. Diego?
Would it be the same for like a calculator? Just like actually that's the point you use the last one as your uncertainty.
No, because that's going to get into what we're going to talk about in a second. The calculator is designed to keep all of the digits, and you have to know where to do the rounding. All right, so, and that's what we'll, so I guess here's a good example. Let's say that the diameter of a circle is 5.00 centimeters, and you want the radius of the circle. We have to divide by 2, right? When you plug that into your, actually, let's say it was 5, not 5.00. Let's say it's just 1 sig fig. When you divide that in half, your calculator is going to spit out 2.5, right? However, this one could be off by an entire centimeter, right? When you divide by 2, we're not going to get more accurate. This one could still be off by an entire centimeter, right? So we actually, even though the calculator gives us this number, we actually have to round it to the nearest 1. Which seems like we're saying that the radius, if the diameter is 5 centimeters, the radius is 3 centimeters. That seems counterintuitive, right? That seems like not mathematically accurate. But if we take into account the fact that this could be off by up to 1 in either direction, our answer could be off by 1 in either direction. So when we say 3 centimeters, we're really saying 3 centimeters plus or minus a centimeter. We're just saying we can't be more accurate than that. So, and your calculator doesn't know how to do that. Your calculator relies on you to provide context for the numbers. Your calculator just gives you the raw math. Your calculator also doesn't do units, right? And so that's why something like the scale has uncertainty programmed into it, but a calculator doesn't. Your scale not only has, it actually has units on there. And so when something also has units, you can be usually fairly certain it also understands, has some amount of uncertainty rules programmed in. So why wouldn't we round that down? If it was 2.4 centimeters, it would make sense to round it down because it's closer to 2 than to 3. If it was 2.6 centimeters, it would make sense to round it up because it's closer to 3 than 2. 2.5 seems like it's right in the middle, except it's not. It seems right in the middle because you're forgetting, if you think about it on a number line, there's 2.1, 2.2, and so on up to 2.9. You're forgetting that there's 2.0. 2.0 to 2.4, you round down. 2.5 to 2.9, you round up. So it actually is, it's not squarely in the middle, even though it looks like it. When it comes to the rounding, a 5 is always going to be rounded up in this class. Any other rounding questions? Okay. Then let's get to more practice or defining these rules. One other point about measuring. We're in the US here, which means I have to talk about fractional scales. I don't like fractional scales. Fractional scales are, instead of having a line for every measurement in between, it divides things into fractions. So a fractional scale is what you are used to thinking about on a ruler, on an inch, the inch side of a ruler, or on a tape measure, right? Because it doesn't have tenths, it has halves and quarters and eighths and 30-seconds and so on. Those have their own rules for measuring. And I'm not going to teach you those rules because we don't want to deal with fractions and then have to memorize a whole nother set of rules for rounding when it comes to fractions. Basically, we're not going to use fractional scales in this class. If you see a fractional scale, like the one on top here, assume that those fractional lines aren't even there. Just ignore them. If you want, you can use them to help you estimate the tenths place, but act like they're not even there when it comes to measurements. If you have, when we're going to use only decimal scales, by which we mean only scales that show you a line for every digit in that place. If it's a fractional scale, assume the fractions aren't even there. So for the top one, we would actually measure only plus or minus a tenth. We'd say 3.6. We would, even though we have those markings for the fractions, we're not going to use them. Ignore them. Right? Other than you might use the half one to say it's more than a half or less than a half or something like that. But I'm not going to teach you the rules for that, for uncertainty and rounding with that, because you'll have enough trouble with the rules that we'll learn for decimal scales. We don't need to add a whole nother set of rules. And even in engineering, in the US, it's still pretty much only use decimal scales. Even if you're measuring things in inches, American engineers will actually do things in tenths of an inch, even though if you go down to the hardware store and buy a tape measure, they're all fractional scales. You get engineering equipment has inches in decimal scales. So you actually have 100th of an inch instead of the 1/64th of an inch or 128th of an inch. So we'll only use decimal scales for this. right? And that means occasionally it gets tricky because some of those graduated cylinders, for instance, will have a mark for 10 milliliters, and then they'll have so basically some of the glassware will actually have a line for every 2 milliliters. That's not a decimal scale because it's not showing you every value. So this one, that's actually a fractional scale. It just divided it up into fifths instead of halves like we normally think about. That means that this piece of glassware could be off by plus or minus 1. Right, so you could still use the line to help you count, but it doesn't count as far as how many digits you write down. Does that make sense? It'll take practice, which is why we have a whole lab just dedicated to measuring numbers. Seems excessive, but again, this is the number one thing, the most common mistake that I see in this class. Not the most significant mistake, but it's the most common mistake. All right. We're gonna do this one now. So this is going through a lot of the same stuff that we just went through on the board. So if you want more practice with it or you want to read it again, see the slides. Key point that I'll say one more time, never give more than 1 decimal place beyond the last marking. Last base 10 marking. Right? Even if it looks like it's right on the line for 3/4, you can't say 0.75. All right, so what do we do when we're adding and subtracting these? Because this is where it gets hazy. It's easy enough to remember the rules when you're actually measuring, but if you're given measured numbers, then you have to do math with them. Now, how do we figure out where to round? And with adding and subtracting, it actually makes a whole lot of sense. When we're adding 2 numbers together, we keep the same uncertainty as your least certain number. So for instance, if I'm going to drive from here to Sacramento and I measure it out in from the circle, the pickup circle here at the high school, and I say it's 112 miles. But I forgot to take into account that I have to walk from here to the pickup circle. Is that really going to change my number? How far off could this measurement be? Plus or minus a mile. Is it a mile from here to the pickup circle? So if I forget that extra, how far is it from here to the pickup circle? I don't know, maybe 0.2 miles. If that, call it 0.2 miles. If I add those 2 numbers together, I might be off by 1/10 of a mile here on the distance to the pickup circle, right? And I might be off by an entire mile here. When I plug it into the calculator, I'm going to get 112.2 miles. But if this one was plus or minus a mile, and this is plus or minus 0.1 miles, how far off is my final answer? Or how far off could it be? By a mile. So even though this is what the calculator is going to spit out, we're going to round it to the nearest mile. Because this number could be off by a mile, so this number could be off by a mile. Right? So we keep it to the same uncertainty as our least certain number when we're adding and subtracting. Right? The other example I use is if your friend is visiting from San Francisco, it's a 4-hour drive roughly from San Francisco to here, barring weather, right? If they gave you an ETA, they said it's going to take me 4 hours plus or minus 10 minutes. If they called you from Placerville to let you know they're going to be late because they got stuck at the light in Placerville and they're going to be 15 seconds late, is that really going to change their ETA? No, because the uncertainty was already plus or minus 10 minutes. they would only need to call you. They wouldn't need to call you at all, but it might be polite for them to call you if they're going to be more than 10 minutes late, because that's outside of your uncertainty, right? Or at least that's the way parents think when they're worried about you taking long drives, right? It took you longer than 10 minutes to get from home to school. Why didn't you call me? Right? Because they have this idea of what's the uncertainty. And if you fall outside of that, then you need to change your estimate. All that to say, this first line up here, when adding, subtracting a measured number, the result has the same uncertainty as the least certain number. Which means sometimes it looks like the result doesn't change. So let's look at these two things. For whatever reason, we're using two different rulers to measure these two pieces of wood. We already measured that first one. The same graphic from the other slide. So we say it was 4.57 centimeters. We're going to add that second number to it. What's the measurement for the second piece of wood there? 3. It looks like it's right on the money, right? But we're going to estimate the 10th place, so we're going to say 3.0 centimeters. We want to add them together. What's the uncertainty going to be in our answer? Where we need to round it? To the 10th place, where it could be off by 0.1 centimeters. So we'll get 7.57 out of our calculator, but we need to round to the 10th place. 7.6 centimeters. All right, I know we're going into fairly exhaustive detail on this. How much of this is review? Have you seen any of this in another class? Some people, yeah, okay. So then I assume you probably also saw the rule for multiplication and division. What's the rule for multiplication and division? Not keep the same uncertainty. Sig figs. And keep the same number as sig figs as the number that has the fewest sig figs. Right, so those are our two systems, our two rules. Addition and subtraction, you keep the same decimal places as your least certain number. Multiplication and division, you keep the same sig figs as your least certain number. Right, and so these are the rules for counting sig figs, but we've already been using that term. But I want to go over this just to reiterate a couple points. A digit is a sig fig, is a significant figure. Depending on your textbook, sometimes they call them significant digits. If it's non-zero, if it's a non-zero number, you can be pretty certain it was measured. Right, so if I just write 7.6, both of those are considered significant figures. They both were measured at some point. We're certain about the 7, not so much about the 6, but they're both measured numbers. So we'd say that this is 2 sig figs. If it's a 0 at the end of the decimal, the only point in writing that 0 is to show that that was measured, right? Like we did with the 3.0 a second ago. So 7.60, that would be 3 sig figs. Is a leading 0 count? No, because we could just add as many of those as we wanted, right? So by convention, you could say the same thing about the zeros at the end. But by convention, leading zeros, by which I mean anything to the left of the first non-zero digit, doesn't count. So if I write 0.0062, how many sig figs is that? Just 2. These ones count. These ones don't. Right? It's still a leading 0, not because we're talking about to the left of the first non-zero digit, not the first decimal point. Right? So anything to the left of the first non-zero digit doesn't count. If it's a 0, but it's between non-zero numbers, that counts. That had to have been measured. And you have examples of each of these. All right, so 5.04, all three of those count. And the last one is one that has very few caveats. If you put it in the coefficient of a number that's in scientific notation, it counts as a sig fig. The only reason to write it in the coefficient of scientific notation, by coefficient I mean this piece here, not the power piece. The coefficient's the part that leads. The only reason you write a number in there is if it's a sig fig. All right, so questions on what a sig fig is. This is great. You've all seen this before, so maybe this will be the first time it's not the number one mistake people make in my class. All right, so just to clarify, what's the uncertainty of 48 meters per second? Plus or minus a meter per second. How many sig figs is that number? 2. If you want a really fast way to convert between miles per hour to meters per second, roughly speaking, you can just cut it in half. Take miles per hour, divide it in half, and you get meters per second, plus or minus 10%. So 3.00 times 10 to the 8 meters per second is the speed of light in a vacuum. How many sig figs? 3 sig figs. What is the uncertainty? That's harder to see, right? Because we're not used to thinking in scientific notation yet. The uncertainty is in 0.01 times 10 to the 8. So we could be off by 0.01 times 10 to the 8, which is the same as saying what? Ten to the 6. Right, this is 10 to the minus 2. 10 to the minus 2 times 10 to the 8 is 10 to the 6. Or just plug it into your calculator and you'll get a million. Sure, your uncertainty is in the millions place. So 3.00 times 10 to the 8 meters per second, you could be off by as much as 1,000,000 meters per second. But that still has 3 sig figs. Right, so with scientific notation, uncertainty gets a little trickier. You have to think about it a little bit more, but counting sig figs is easier.
Uncertainty, scientific notation. So like, can I put the uncertainty as 1 to the 10, or like 1 to the times 10 to the 6?
1, yeah, you can write plus or minus 1 times 10 to the 6, and then that's really explicit. If you don't write it though, we can always assume, unless otherwise stated, that you're plus or minus 1 in your last sig fig. Right? The only time you need to write the uncertainty is either if you have an ambiguous number. Like if I wrote 100 miles per hour, is that plus or minus 100 miles per hour, or plus or minus 10 miles per hour, or plus or minus 1 mile per hour? It's unclear, right? So in this case, you could either rewrite it as scientific notation, or you could explicitly write plus or minus 10 miles per hour. That's a full credit answer too. Or 1.0 times 10 to the 2 miles per hour. That's a full credit answer too. This is probably the more common way to do it. When you get used to it, it's actually a lot easier and faster to just do it like this than it is to worry about writing your uncertainty out every time. All right, last one. Speed of sound. How many sig figs? 5. And what's the uncertainty? 0.01. Our uncertainty is in the hundredths place. So we could be off by 0.01. And if anything, that's overrepresenting because the speed of sound depends a lot on atmospheric pressure. And atmospheric pressure, even at sea level, can fluctuate by as much as a couple percent day to day. So if anything, this is actually probably too many sig figs for actual speed of sound. All right, questions on sig figs and uncertainty? All right, so this is practice with scientific notation. I'm going to skip the first part. Because I'm going to use the time to talk about diameter of the sun versus diameter of the earth. Basically, one of the reasons that scientific notation is really, really helpful is being able to eyeball and do rough mental arithmetic in your head. If we have the diameter of the sun and the diameter of the earth, if we want to know approximately how many times larger is the diameter of the sun than the diameter of the earth, and when I say approximately, I mean don't use a calculator. In your head, how much larger is the sun than the earth? And how did you do that?
It's the difference of the powers.
The difference of the powers. Yeah, 1.39 and 1.27, those are pretty close to the same number in the coefficient, right? But those numbers, 10 to the 4 and 10 to the 6, off by a power of 2, right? So you have a difference of 10 to the 2. When you actually do these numbers, you're going to get something close to 1 for your coefficient, and you're going to get times 10 to the 2. So roughly 100 times larger. So thinking in terms of orders of magnitude, based by which I mean powers of 10, can be really helpful when it comes to doing those reasonableness checks on your calculations. Right? You should always be able to estimate within a power of 10 before you hit enter on your calculator, especially if you're doing everything in scientific notation. All right. Let's this is what I want. When we're multiplying and dividing with sig figs, this will be good because we'll get through all the dry stuff and then we can move on to more fun stuff like conversions and spending more time on conversions. I say fun and everybody grimaces. Conversions actually are maybe not fun, but useful in everyday life when you get good at them. This maybe not. It still makes sense with everyday life. But anyway, when it comes to multiplication and division, we keep the same number of sig figs as our least certain number. So let's say we had a box that was 12.10 centimeters long, 14.58 centimeters wide, and 3.1 centimeters high. I'm missing a unit on that one. Whoops. If we want to know the volume of that box, that's going to be length times width times height, right? But that means when you plug that in to your calculator, you're going to get this big, long number. Our number is not actually plus or minus 1 times 10 to the minus 5. Not actually that accurate, right? And so we can't just keep the same uncertainty as before because this number is a lot bigger than it was. We keep the same number of sig figs as our least certain number. So 12.10 centimeters has 4 sig figs. 14.58 centimeters has 4 sig figs. 3.12 centimeters is only 3 sig figs. So we're going to keep 3 sig figs in our answer. Right, so we're going to round to wherever we need to so that we have 3 sig figs left. So that's going to wind up being 550 plus or minus 1. Right, and so here's an example using that decimal place to indicate that it's plus or minus 1. A better way to write that would be 5.5 times 10 to the 2 centimeters cubed, or 550 centimeters cubed plus or minus 10 centimeters cubed. That's still a full credit answer, but that's less universal using that extra decimal place. All right, so any questions on multiplication and division? All right, let's do one where I don't like that example. I like this one better. Let's do one where we have to do both rules together. So this isn't the dimensions of this room. This is the dimensions of the room that I teach in all the time at the college, or close to them. They're estimated numbers. So our classroom is 32.5 feet by 16.0 feet. What's the area of the room? We're going to multiply length times width, right? 16.0 feet times 32.5 feet. Easy enough, right? Our calculator answer gives us what? Say it again. 520 feet squared. How many sig figs do we need to keep? 3, right? So 520 plus or minus 1. And then let's say that a chunk of this square feet is taken out. Let's say they install the bulkhead for ventilation. And the bulkhead takes up 6.00 feet and by 1.55 feet. How many square feet are lost? Still just length times width, right? So area lost be 6.00 feet times 1.55 feet. What's the answer we get there? 9.30 feet squared. What's the new area of the room? Well, we had plus or minus 1 square foot here, and we're subtracting a number that's plus or minus 0.01. So this is what I mean by when we switch operations. When we do the subtraction, we have to already have them rounded properly before we switch the subtraction. So 520 feet squared minus 9.30 feet squared. Our final answer is going to be plus or minus what? So it's going to be 510.7 feet squared. That's our calculator answer, right? But we could be off by an entire square foot for our first answer, which means we've got to round to the ones place. So our actual final answer is 511. It's fine to write this number in, just don't box this number. Do your rounding and then box your final answer after you've done your rounding. And if you kept all of your digits from these first parts, you wouldn't know where to round at the end, right? So the point of rounding before you do the subtraction is that you know where your uncertainty is for these two numbers. And then you can do the subtraction and round to the right spot. All right. That's good for today. You guys can pack up. And it'll be more interesting on Wednesday.